So what we're going to do today is actually probably step away from the code for a bit and think about. I haven't come up with a better way to do that yet. Let me open just humble paint and think for a second about the simplifying algorithm, right? Because that's what we want to. I'm gonna have a better setup with this pen. Okay. So in general, we're gonna have. So we can have, a simple case is like. Can I just? So simple case is just like 0, 0, 1, 1, right? And I think if I put them in a matrix form, that makes a lot of sense. That's just like that's just the Bell state, okay? So, and each of these branches have like their own amplitudes. Maybe we'll just put them. So if this will be alpha and this is beta, maybe we could put them in the matrix as well. And so I need to know what I can merge that, right? So I think the way the signature is going to look like in terms of the algorithm signature is that that's qubit 0, that's qubit 1. Maybe I should transpose this. Maybe it's going to be easier to process because I can go array by array, because I want to merge things this way, right? So I want to compare this element with this element, this element with this element. So maybe I should just. Is there a way to make this bigger? Can I just make the rubber bigger? Somehow. Or should I just select the whole thing? Yeah. And so say here we have qubit 0, here we have qubit 1, and then here we have sort of the branches, right? And then what we wanna do is we're kind of merging downwards. So this is like this is like that exactly. So, and this will be alpha and this will be beta, and sort of the algorithm goes down this way comparison wise, right? So and remember so what I'm trying to achieve here is try to see if we can, whether we can simplify these hyperedges by putting things together. The way that we simplify hyperedges is based on the way that I'm doing it just intuitively, and I don't know if that's correct or not, is that, or at least all the elements but one must be the same. I mean, if they're all the same, then it's obvious, right? If we had a like 0, 0, 1, 1 like these, right? Qubit 0, qubit 1. So, I mean, that's like you would compare 0 and 0, they're the same, 1 and 1, they're the same. So the two branches don't make sense at all. So you just have these values. But if you the trick is if you go to 3 qubits, right? Q0, Q1, Q2, and then you have, for example, 0, 0, 0, 1, 1, 0. I think I'm doing it correctly, 1, 1. And then this qubit is, for example, all in the plus state, right? So, I mean, you can obviously see that this can go out in its own branch, but we got to treat the entanglement as as a tripartite entanglement. Like it's not, you know, two pieces. It's not that Q0 and Q1 are entangled and then Q1 and Q2 are entangled. Is that the three are entangled. And so the way you would do that is, so I would assume is, and applying the same rule, there must be all at least, not at least all minus all but one must be the same, right? So if we take, for example, this row and this row, the 0 and the 0 are equal, the plus and the plus are equal, so they can merge. They can merge because then if you have alpha and beta and p and q or whatever as the amplitudes, right? So essentially these two can be summarized into alpha, into 0 and to alpha 0 plus beta 1 and plus, like in this branch, right? And the same happens here, right? So here you're gonna have two steps. So, but you can merge them because they're all the same but one element. I think I'm not gonna think too much about it in terms of whether there's any other way to do this. If anyone knows a better way, then welcome for improvements. So there's a 1 here, and you would kind of have the same, right? So you would have a P0, and you would have a Q1, and then you would have a plus, right? Now, so that stays like that if, you know, if these four amplitudes are different, that stays like that. Now, if alpha equals P and beta equals Q, right, then essentially these two nodes are also the same. And so we can apply the same rule, right, and say plus plus is the same, these are the same, and so, you know, okay, but what are the alphas and no, I think I've done okay. So I shouldn't move these things here unless it's one branch left. What I should do is I should no, actually it is important. I actually have to move these, right? But I have to move the alphas and the betas because they belong to these specific elements. But now I don't have alpha and I don't have an amplitude for this branch or an amplitude for this branch. How can I calculate, like, where are those? How can I calculate them? Have I just missed them, or just 1 and 1? It cannot be just 1, 1. Or are they alpha plus beta? Maybe that's because we are adding the things. So my wild guess is that if this is like R and V, that R is alpha plus beta and V is P plus Q. That's my wild guess, not knowing what the hell I'm doing. Because essentially I'm adding these elements, so I should add the amplitudes as well, but those kind of go down here. And I think at least it works for the case where where this is like No, no, no. Yeah, where this is like these. Oh, what am I doing? So if this is an equal superposition, right? If this is an equal superposition of 4 elements, then this should be 1 divided by 2, and this should be 1 divided by 2, right? Yeah, because then it means that each of these branches have like a 0.25 probability. And so I guess what I should do is add them plus normalize. So they'll both, they'll both add up to 1. So they'll add to 1, they'll add to 1. But then if I normalize, I could just go back to being 1 over the square root of 2, 1 over the square root of 2, which is what we want to have, because, yeah. I think we'll have to experiment a lot with these later, kind of have different wave functions and just build tests out of these. But it seems like that's what I should do. Cool. And so, and kind of the same, and now you check whether you can apply the same criteria until you just have one. So it seems like we could do some sort of recursive method. I mean, the way to pick these is like the way that I envisioned it here is like the signature is the qubits, right? So, and that is not just 2 qubits, but it's like an array of qubits. So that's fine. I guess we just have to make sure that then the edges don't have more qubits, because in that case it's an error, right? It has to be like exactly these. If these are still entangled with a with like a Q3, like a 4th qubit, then there should be like an error, right? Or if they are not all entangled, like then that should also be an error. But for now, we can just, so here I should just be putting them into the matrix, right? Build a matrix and check if exactly all the qubits are entangled, are in hyperedges. Remember, it doesn't necessarily mean that they're entangled, because maybe the simplify will lead to us, maybe I just call it simplify and expand, because it's not that we're simplifying the entanglement, we're simplifying the hypergraph. And so what we should do here is call recursive part. Call the recursive part, exactly. So simplify recursive. I don't know what is it gonna what is it gonna have. It's gonna actually have the matrix, right? The matrix M, we'll call it. The hyperedge matrix. That's what M is. And so I don't know what it returns though. What does it return? Yeah, it returns another. It returns. Well, I guess, yeah. That's kind of the thing, right? So if the matrix is just gonna have one row, right? That's sort of the base case. So so either the matrix has just one row, in which case it's done. I guess it returns, well, it will return a matrix, right? So it will definitely return a matrix, and then process output matrix, and then here we'll decide what we'll do with it. I guess if only one row, for example, all nodes go to system, right? If more than one row, then rebuild hyperedges. I guess that's what we do. That's probably the way this works. Right? If we just have one row, it means we've simplified it so much that it does not actually have entanglement. But if it's got more than one row, then it means that there is entanglement. Okay, but what do we do? Still, there's something. Like, what if we stay here, right? And that's the output matrix, this one here. So we have like R. So we have like qubit 0, qubit 1, qubit 2, and then we have, let's say alpha and beta, right? And then we have 0, then we have like, some sort of like, yeah, that's the wrong, but like A0, B1, and then C0. Right, so what if we output these? Okay, so what I think we can't compress that anymore, right? Because there's no elements like that, but we can definitely split these, right? Because that's not entangled. Okay, so maybe what we should still do here is check. First of all, it's like check if columns, if one, so simplify columns, right? All equal, no entanglement. So all elements equal, no, within a column, no entanglement, exactly. Because then we should just take that column from there. Yeah, and I think here probably just building a NumPy array makes a lot of sense. But I think that's a good idea. So so we built a matrix. We call the recursive part. And so what the recursive part is going to do is it's going to check. It's going to do one pass. It's going to check through all possible combinations. These with these, this with these, this with these, this with these, but like, of course, without repetitions. And then if they're equal, then we will just be building a new row in the result column. Yeah. Yeah. And then the resulting matrix, it will just be passed again. And so the way the recursion is going to finish is that if no new row has been built, or right, so the way this will be like that is that if well, definitely, like, if only one row return and return m, right? Do one run, and if basically if n is empty, so no new row has been simplified, return m. Yeah, well, I might as well just not to have this too complicated. Because if it just has one row, the do one run will just be trivial. So it's not that I'm doing here some extra cost or anything. Do the run, recursive call. So simplify with n, exactly. Okay, cool. I kind of like it. Let's get to it, I guess. So I guess so. Maybe I should save that. Wait a second. Because it's not a bad way to think about this. So we'll save this in so far in desktop. Simplify on go. Okay. Cool. Perfect. Let's get to it then. What do we do first? So we build a matrix, right? So qubits, it's yeah. So we need to get the edge intersect, right? No. What do we need to do? What do we need to do? So we need to build the matrix. We need to get all the edge information. Exactly. How am I gonna label these correctly? How am I gonna label these correctly? Make sure that I have the right qubit, because at the end of the day, people can give qubits whatever names they want, right? So, okay. I should just populate these as we go. So I should probably have a so for qubit, for q in qubits, right? So now I'm processing one qubit, like the first qubit. So what I do is I need to get the edge IDs. So edge IDs for this qubit. For Q. And once I have these, then I can actually have so these are the edges in which the qubit is in, right? Well, first of all, how do I do? So I want to have, like, do I have NumPy in here? I think so, right? Yeah. So I want to have NumPy empty. Yeah, I keep forgetting how to do that. Simply, maybe I don't have to, but so I have the edge ID. So now I wanna, so these are all the edges this qubit is in. Okay. Now, so this will dictate. So now I'm gonna kind of fill up a row, and that's gonna dictate, I think. That's gonna dictate. Am I able to figure out on the fly whether there's a mistake, whether the qubits won't, whether the specified qubits actually won't work because maybe there's, they're not all entangled and stuff like that. Probably. Maybe I shouldn't. I don't have to. I don't think I have to have a matrix, to be honest. I think I'm better off just using dictionaries. Dictionaries of dictionaries. I think it's going to be easier because then I can access these. So I can say, yeah, probably with matrix will be more efficient. But I can just build a dictionary of the edges now, and then yeah, and then basically put the nodes. Yeah, so I can actually have a. So this is M, right? And it's an empty dictionary. Then what I do is I say for E and in HIDs. I'm not trying to make this efficient right now. I just want to make it easy to code, and I just don't want to make stupid mistakes. So I'm just not good at this stuff. So for each edge ID, right, I do M ME equals, and now this is an empty dictionary. And what I need to do is I need to do for, oh no, what I need to do is I need to do, so ME is an empty dictionary where I put the, yeah, now I need to go through all the nodes of this edge. Oh my god. For n, for node, or for n in self edges e node UIDs, right? So I now need to go through all the nodes of this edge and check the one of that qubit. And so if n dot qubit equals q, right? So m, basically m e q equals, and now I have to put the state in here. So n state. Okay. Yeah, I think that makes sense. Right. So this means that for each qubit in here, I'm building a dictionary of its edges, and then this edge is being populated in here when I created it. Okay, but that's wrong, so I have to check. If E not in M keys, right? So if it's not in the keys, then I gotta create it. Then I go through all the node IDs of this edge, right? And of course, this edge will have multiple edges. This qubit it has nodes in, and then I basically, yeah, and then I basically if the qubit is Q, put the state in here for that particular qubit. Okay, let's see. Let's just return M and see what happens, right? So what do I have here? Simplify. So got this. Oh, I gotta do everything. The imports as well. This and this, and see what happens. If I get the right thing. And then how can I check? How can I check whether these is a correct? Oh, okay. Qubit. It's not actually qubit. Oh, yeah, sorry. That is actually should be self nodes n. There you go. And then the same for the state. Yeah. Oh well. What about print m? That's stupid. Wait a second. I should not. This shouldn't return anything. Simplify shouldn't return anything. I just want to print. That's it. Print m. Okay, so edge. So edge 0 has a qubit. Edge 8 has a qubit 0 with a state 1, 0, and a qubit 1 with a state 1, 0. And edge 11 has a qubit 0. 0. Actually, yeah, okay. No, that's correct, I think. Now, the problem is, how do I detect? Okay, so what if I do, how do I detect, for example, that, if I just, I know it's a stupid example, but if I just want to do these, that tells me that it, Q0 is in these edges, but I want to know whether there are other qubits entangled that are not in here, because then that's dangerous, right? I guess one way to do this is while I'm iterating in here. So so I guess what I should do is so error false. And what I should do is, for example, if while I'm iterating over the node IDs, right? So if this qubit not in qubits, right? Then the error is the or error true, or error is that the qubits are entangled with others not specified in the input, right? Exactly, that's one thing. And then another error that I need to catch is if the if I give too many qubits, right? So this means if well, that is actually here, right? Because this is, so if the edge is not in here, it means that some of the qubits that we picked up are okay. So if E not in M keys and how do I differentiate that? Like, if this happens for the second qubit, I guess I should just I can do a first pass on the first qubit, right, and say, or I can just say if the index of Q is not, no, that also, yeah, maybe. Because after the first pass, I pick the edges of the first qubit, and then if I catch another qubit that has another set of edges, yeah, then it's an error, right? So if I'll just say, I don't like this, but like first qubit, or it's easier if I just like n what's it, index of what is index of Python index of Python list index of n qubits index of Q equals 0. So if we're still processing the first qubit, then it's okay. You know, so else is it else-if or elif? Python elif. Keep forgetting. Thing is elif. So if this is still the case, then an error. The input qubits or the qubits are not entangled together. Exactly. So what I want to say here is that if error, print error, else print m, or I'll just print m regardless. Elif else, yeah, okay. So that should give me an error now. The qubits are entangled without this not specified in the input. Exactly. If I is this going to break? I have no idea. Well, it seems to work But now it says the cubes are entangled with others not specified in the input. That's not. Yeah, sorry. If I will do Q1 and I will do Q2, now it's going to tell me. Okay, that's not correct. Edge 2. Okay. I would expect an error here. I would definitely expect an error. I expect this error. No, this error. Wait a second. Yeah, exactly. So what am I doing? So I'm doing if the E is not in keys and the qubits index, is this the way this works? Qubits index, list index element. One, okay, yeah. So if I print E, if E not in M keys, so print E here. So okay, so it's at least it's not getting in here. Is it processing? But it's not processing system. Oh, because there's no edge. Oh, because I'm just adding that. Okay, I'm adding that just for representation purposes, but I don't have an edge. So, okay, so there's another error to catch, which is that if so if length of edge IDs equals 0, right? It means this qubit is not entangled. So it means, so I'll basically say one or more qubit, or just the same as one or more qubit is not entangled. I could say which one. So qubit Q is not entangled. You can say like this. Qubit Q2 is not entangled. Okay, cool. That works. Perfect. Okay, great. So I think that gives me the matrix that I want. I want to have just 2 qubits back again and stay within the ranges of something that works and that doesn't spit out an error. And I think I'm gonna call it a day. So now it's like that. Okay, cool. So now I have it's not a matrix, but it's a dictionary, but it's fine. I can treat it aside. So I have M, and now I can. But that's even better because I think it's going to allow me to process the output a bit more, a bit in a bit of a simpler way. So now I basically, call these. So I get basically a result, and I kind of so need to process this, and then Yeah, exactly. That's awesome. Cool. So the matrix is built. Gonna leave it here today because I gotta go do something else. But at least I'm happy that um, that I have got, I think, a relatively good algorithm for these. And so the expand part is going to be interesting as well. So it's going to be sort of the inverse of these, right? So where I take, I'll build the same matrix and see if I can expand it. This means that that if I have these, right, that I can actually build these. So basically splitting these elements, which are the elements which are not equal, splitting them if possible. So it's going to be a z-axis expansion, right? Maybe I should call it this way. Well, it's just going to be a z-axis expansion. So it's going to expand from a 0-1 perspective. So if we've got like a plus state, we're going to split it into two branches. You know, you could do an x-axis expansion where if you would have like a 0 state, you would expand it into a plus and a minus state. But that's yeah, could be a nice exercise. Cool. Okay, but this is good enough for today. Good progress. Good progress.